Hello students, this is lecture number 32 and we are studying chapter number 9 and this is about 2D elasticity problem. In the last class we derived the strong form, okay, and the strong form is something like this. So in a scalar form we had del sigma xx plus divided by del x plus del sigma xy del y plus bx equal to 0. Okay, this is in equilibrium in x direction. Then we had del sigma xy del x plus del sigma yy del y plus by equal to 0. So together they constitute the strong formulation. Yeah, okay. So this we can also write in vector form, and we said like this: divergence of sigma x, yeah, plus bx equal to 0, and divergence of sigma y plus by equal to 0. Exactly same equation we have this one. So of course where sigma x is nothing but sigma xxi plus sigma xyj and sigma y equal to sigma xy I plus sigma yyj. Okay. Okay, so this is what we got last time. We can also write the same thing in terms of a matrix system. So here we are treating this as a vector, so we have divergence basically, and this is important to write like this one because we can apply divergence theorem, you know. So this is what we will need, but still I'm going to also write in the matrix form. So basically all the same thing, this or this, yeah. So maybe I just do like this one, different formulation. It is exactly the same thing, all are same, yeah. So basically it is the same thing. So this is one way of doing it, writing it. This is the second way of writing it. Okay, there is also third way, and third way is to write in terms of vector, in terms of matrix, and this is del s t, and then we can say sigma tilde plus b tilde equal to 0 tilde, where b tilde is nothing but bx by. So yeah, 0 tilde is nothing but 0 0, yeah. Then delta, this del s is nothing but, so we have del over del x, then we have 0 del over del y, then 0 del over del over del y and del over del x. Yeah, and here this is what del s is, and sigma tilde is equal to sigma xx, sigma yy and sigma xy, so that del st sigma tilde will be equal to this del over del x 0 0 del over del y, then you have del over del y del over del x multiplied by sigma xx sigma yy sigma xy. Yeah, and this will be equal to, this will be like sigma x del over del x del sigma xx over del x plus del sigma xy del y. This is what that will mean. And similarly here this will be this multiplied by this, so del sigma y by over del y plus del sigma xy over del x. Yeah, okay, so this is what the meaning of that. So this is the third form, so we can write this is the third form. All the similar one, right? This is the first form, this is the second form. Yeah, so we can write the same thing in three different forms. Yeah, and all of these are subject to essential boundary condition. Number one, essential boundary condition, and that means we are giving on some boundary gamma u, on gamma u, what is given? U equal to u bar. Yeah, okay. And second in natural boundary condition, and this will be on gamma t, t for traction. We found out what is the meaning of traction is. So on those there we have the traction given. Yeah, so we also know the meaning of traction, and that is we just wrote sigma, or this is like this. So we have sigma xx, sigma xy, sigma xy, and then sigma yy, and nx ny equal to given is tx ty. Okay, so this is given at those boundaries. Yeah, so meaning that sigma x value, sigma xy value multiplied by n, and where n is the perpendicular to the boundary. Which boundary? Gamma t. Yeah, this is n, unit vector basically. So this n is equal to nxi plus nyj, and this is the tensor form of this one. Yeah, so we can also write if let us say if you call this as tau, tau tilde, this one is n. Yeah, and this we call t bar. So same thing we can also write here in different notation, tau tilde n okay, okay, not n, let's say n tilde equal to t bar, equal to t bar, yeah, and where the t, or let's make write t tilde, so that where tau equal to this, n is equal to okay, so this is not n, so this is n tilde and this is t tilde, so we will write t tilde here like this, yeah. So same thing we are writing here in short form basically, yeah. So but this is what will be given in the boundary as well, where the forces are given, so it will be given like this one, yeah. Okay, so all those things we have worked in the last video lecture, so I just given the recap here, so that we can use these things, okay. Now the given these strong form, the next step is to what is the weak form, okay. So to derive the weak form, the strong form that we are going to use will be the one which has divergence. So divergence of sigma x plus bx equal to 0. Okay. So let's use this one first. So and what we do, okay, here's the finally we have to write this in terms of u also, okay, but right now let's not bother about it, okay. So eventually we have to find out the relationship, like we have to find out sigma x as a function of u, right, ux and uy, we have to find out like that, yeah. But let's derive the strong form first, weak form first, and then we will go back to see how sigma x is related to ux and uy, where these are the nodal, ux or uy are the not nodal but the displacement. What I mean to say here, in this case u xy is the displacement that we need to find out, because sigma x is a function of ux and uy, and this is what we are going to put some test function. So this is what test function will be, okay, and we will assume it to be to be a polynomial as we have done earlier. We will come back to later, okay. Polynomial meaning that this could be example, I am just example will be u x y equal to 1 plus alpha x plus beta y, for example this plus gamma, right. So gamma plus alpha x plus beta y, it could be something like this, where we have 3 variables to be found out, and you know, just 3 variables here, so it will be suitable for a 3 noded element, yeah. So their test function will be like this one. However, remember that here we are also, it is not a, this is not a scalar anymore, yeah. So exactly what we are going to write is, there will be this will be also a vector. So this is a vector, remember, so this is a vector, so this will also vector, this will also vector, alpha also vector, beta also vector, meaning that we will have ux is equal to gamma 1 plus alpha 1x plus beta, right, beta 1 y. We will have something like this, yeah, and u y will be also like gamma 2 plus alpha 2 x plus beta 2 y. Yeah, so what I mean to say is here that this is a these we have to find out, like these are the one which are test function, these are the one which are variables, and hence we have to like we have some equation which will be something like this one. Now if the test function is of this nature, our u w like weight, right, weight function w will also be a vector, and it will be like will be w x I plus w y z. So what I mean to, if u x y is equal to u x I plus u y j, yeah, then if this is the test function which is something like this one, w will also, w is also a vector. If u is a vector, u is a test function, is a vector, the w will also be a vector, so it will also have two components. So this is important to understand, because when you are going to use this one, we have to use some wx, where since this is about the x component, then we have sigma y by, there we will use wx wy. Okay, so that's what I mean here, why we need to have different weights multiplied here. So let's start with the first one, and this is divergence of wx, sorry, not wx, not yet. So sigma x plus bx equal to 0. Now multiplied by wx, now just multiply by wx, and we have bx, right, okay, and we are going to integrate over the whole domain like this, okay. Okay, so now we are going to use some identity as we did earlier. So what I mean to say is, this divergence of wx times sigma vector will be equal to what? We will have divergence, so this will be basically the differentiation by parts. What it means, we can see here. So this will be sigma del over del. So we have done already, so still I am going to do here. So I plus del over del y j, and then dot, and we have wx, and then we have to multiply by what? Sigma xx I plus sigma xy j, right, okay. So equal to, so we have I dot I here, j dot j here. So what we find? We find two things basically. So we get del over del x and wx sigma xx plus del over del y wx ws sigma xy, yeah, and which will be equal to, so we will have del x sigma xx plus wx del sigma xx del x plus del wx over del y sigma xy plus wx del sigma xy over del y. Okay, done. So then what do we get? We get is equal to, so looking at this one, we have sigma xx here, so okay, so what we see here, wx here, and then we have this plus this gone here, and here wx wy del wx over del x and del wx over del y. So just a minute. Okay, so xx we had wx yx here and like this. Okay, so we can combine this and this and this and this together, and we can see what the meaning of that. So basically here we get del wx. So let's write like this one. So we are going to combine. So this and this is what? This. So first we are going to write which one? So we will write this one. So this plus this will be the first one, and this we can write as gradient of wx, okay, dot sigma x, okay, right. So gradient of wx will be del wx over del xi plus del wx over del yj dot of sigma xxi plus sigma xyj, right. So like this. So this and this is done. Next thing is this. So what we see, plus wx and see what do we see here. So this and this, so we can, this will be gradient. So this will be simply gradient, divergence of sigma. So now next is this and this, yeah. So okay, so next thing is this one and this one. So combining together we can write here. So will be the wx, so wx common, and this plus this. This plus this is nothing but divergence of sigma x. So we have here divergence of sigma x. Yeah. So you see, this is the what this term is. If you look here, this times this is nothing but this times this. Yeah. So that means we can find out. So what we got here is, we can write in red here. So what we got is divergence of wx sigma x is equal to gradient of wx dot sigma x, okay, plus, or rather let's write the final what we are going to use. So this will be, what is the meaning of this one? So this will be, so so Wx divergence of sigma x will be equal to divergence of Wx sigma x minus gradient of Wx dot sigma x. So this identity we are going to use it here. Yeah. So here one thing we forgot, so we write this equal to 0. Yeah. So this is whole thing is equal to 0. So this integration over whole equal to 0. This is what the weak formulation, right? So this one is weak form. Okay. Okay. So right. So weak formulation is, so we will have whole domain, and then we are going to write this one. So Wx multiplied by this, which is equal to Wx multiplied by this whole thing is equal to this one. So we are going to write the whole thing, this one. So gradient of Wx sigma x, so gradient of Wx sigma x, okay. So gradient of Wx sigma x minus sorry, divergence of Wx sigma x and minus gradient of Wx times sigma x, gradient of Wx dot sigma x minus gradient of Wx dot sigma x. Yeah. Okay. Plus, not to forget, it had second part bx. So we write Wx bx d omega equal to 0. So this is what we got. Yeah. Okay. So this is just taking the x, this one is just taking the x the balance of forces in the x direction. Yeah. So similarly we can also write that similarly in y direction, basically means the taking the second one. Our second one is gradient divergence of sigma y plus by equal to 0, right? So if we multiplied by wy and then we do the same operation, then what we get? We get omega, then divergence of wy sigma y, right, minus gradient of wy dot sigma y d omega plus wy by d omega is equal to 0. Yeah. Okay. So we got this. So we got number 1 equation, this one, the number 2 equation is this one, and we are going to combine them together and we will see what is the meaning of that. We can also simplify it further, so that will help us to combine these and these two equations. So what you see here is the divergence of this. So this will be this value, we can write it also here. So what I mean to say is the value which is this divergence of Wx sigma x yeah, and times d omega. So this d omega will be equal to simply, we have to just replace this with n, right. So this will be n dot like this, or this dot n. So it will be simply wx n, sorry, wx sigma x dot n d gamma, okay, and this will be the like the closed integral, yeah. So this will be closed integral of that. So this comes from the divergence theorem, okay. So this is because of the divergence theorem, yeah. So this is okay. So we will apply the divergence theorem. So from here we are writing like that, yeah. And similarly same thing we can apply here too, and we can write this equal to w closed integral wx and sigma y dot n, where n is nothing but the unit vector perpendicular to the boundary, yeah. So let's write that, and from 1 we get, so from equation 1, okay, and we write the divergence with divergence theorem, and what do we get? We get this one, yeah. So closed integral wx sigma x dot n, okay, and d omega, okay, that's one thing. Then we have minus, so this we will have it for the whole thing. Oh, okay, there is one thing wrong. So this will not be omega but gamma basically, yeah. So this is for the whole gamma, okay. And then we have minus, and then we have gradient of wx dot sigma x, yeah. This integrated over the whole domain, okay, plus wx px d omega, again omega, yeah, is equal to 0, okay. Similarly from 2 we will have closed integral over the whole gamma wy sigma y dot n d gamma minus omega gradient of wy dot sigma y d omega plus wy by d omega is equal to 0. Let's simplify further. So let's call this as equation number 3 and this equation number 4, yeah, so that we can refer later on. But what we're going to do is simplify, we are going to add them together. So equation number 3 and 4 we are going to add together. Okay, so anyway, there are some common links. So for example, sigma x have sigma xy, and sigma y also has sigma xy. So that means both are linked, basically they are not independent, and hence we have to combine anyway. So let's look at this. So can we add them together? So whenever we say 3 plus equation 3 plus equation 4, so we will see that this multiplied plus this one. So if we add them together, what do we get? So we can see. So Wx sigma x dot n, right, okay, dot n plus wy sigma y dot. So I am not making any difference between this hat and vector. Basically both are the same thing, basically both are the same thing, so remember that. So what I am saying is n equal to n, it is the same thing, yeah. So it is the same as this one. Okay, so this is equal to what do we get? So here we can write it as like this, is equal to say combining them the two, it will be a scalar number, right? So we can write like this. So wx wy, right, and then we have something like this. So sigma xx sigma xy sigma xy sigma yy, and then we have nx ny. Yeah, so you see here, this one is 1 by 2, this is by 2 by 2, this is 2 by 1, hence all a scalar. So this is what it is, the whole thing will be like this one. And this we can write it as, let's call this one as is w tilde transpose of that, transpose because w tilde will be equal to wx wy in vector form, and then we have this, we call this tau tilde. So this is what is that? This is n tilde, this one, yeah. So this is n tilde, yeah. So this is what the whole thing will turn out. So if you add this and this is what we will get, this one. Okay, now the next one. So next one we have this and this, that we can combine together. So let us see. Okay, so before that we can do this one, w, write that. So wx, so let's use different color now. So wx bx plus wy by is equal to, we can again write wx wy, okay, and then we have bx by, and again we can write is w tilde transpose and then b tilde, yeah. So we can write like this one, yeah. So if we combine this and this, we can write simply like this one. If we combine this and this, we can write simply like this one, okay. So okay, one thing we forget here, so there will be a tilde here as well. Okay, so we got this and this covered, this and this. Now only thing is like this one, if we add this and this, then what happens? So this is gradient of wx dot sigma x and all. Okay, so gradient of wx dot sigma x plus gradient of wy dot sigma y, yeah. Okay, so what does that mean? So let's expand it, let's see what is the meaning of that. So we can have is equal to we will get del wx over del x I plus del right, del wx del y j and dot sigma xx I plus sigma xyj, yeah, and similarly this side too. So del wy del x I plus del wy over del y j dot sigma xy I plus sigma yy j. So this is the full extension, yeah. So finally we will get it as sigma wx over x sigma xx plus del wx del y sigma xy del wy del x sigma xy plus del wy over del y sigma yy. Okay, so what do we get? So we can see here we are basically sigma xx xy xy yy, we have x here, y, x here, y, and so on. So if we want to write in some sort of matrix form, then how can we write? So we can write it as we have sigma x, sigma xy, and sigma yy term. So that we can have probably here. So let's write it like something like this one. So okay, maybe here. So we have sigma xx, sigma yy, sigma xy. Oh, yeah. Okay, so although we want okay, this is 3 by 1, right? So this is 3 by 1, so this will work because this is going to, we are going to multiply, and here what will be there? So let's see, just we will see. Okay, so here we will get sigma xx, we have sigma xx only once, so we will write del, so del over del wx over del x, so this multiplied by this, then we have yy, so del wy del y, so del wy del y. Then for this one we have two things, so del wx del y plus del wy over del x. So let's write in different color. So del w del wx del y plus del wy over del x. Yeah, so we have these three members, this one, this one, this one, yeah. So we can also write it as like this, so is equal to, so 3 we can write like this, so 3 by 2 there will be sorry, this, okay, just write it here. This is 1 by 3, this is 3 by 1, so we multiply like this one. Now let's write 1 by okay, so this one we can write differently. So let's see how we can write this one. Okay, so the same thing, if you want to write, then how will you write? So we will okay, so we will come back to here. Okay, so in the next page, let's find out what is the meaning of this one. Okay, so basically what we are looking for is this one. Yeah, so I'm just transpose it and we can write like this. So del w x over del x, del w y over del y, and del wx over del y plus del wy over del x. Yeah, so this is 3 by 1. So we can write this as, first we have 3 by 2, then 2 by 1. So we write something here which is 3 by 2, and then we write something here which will be 2 by 1. So we will get that. How? We write in the same form as we have seen earlier. And what is that? So this is, we are going to write here, and here we will have wx wy. Yeah, okay, and so here we will have del over del x 0, 0, del over del y, and then we have del over del y, del over del x, and this we called del s. So if you look earlier, this we have called del s. Okay, del s tilde. Yeah, so this is del s tilde. This one is w tilde. Yeah, so basically this matrix, this one will be equal to, so just write it here, is equal to del s, del tilde s, ws, and transpose of this will be transpose of that. So if you see here, this one is nothing but, this is the transpose of this one, and hence this will be this will be transpose of this, the whole thing. Okay, del s w. So that's write it here. So we have del s w tilde both, transpose of that, and then we have sigma, yeah, tilde, and which means this we have w transpose, then del s tilde transpose w. Okay, so this is what we get. Okay, so that means we have combined one. So one thing is this one, yeah, okay, sorry, I think this will be sigma. Okay, this is sigma. Okay, so one thing is this. Okay, then we have this one, and then we have this one. We get three things. So we will combine them together. So this is integrated over the whole boundary, and all the two are integrated over the whole domain. So this is w transpose tau n, w transpose tau n. So combining them together, we get w transpose tau n, okay, this is d gamma, and this is the boundary on the boundary. Then we have the second one, yeah, and second one is this one. So this one is a W transpose del S transpose sigma W transpose del S transpose sigma. So W transpose del S transpose sigma, and this is over the whole domain. So this is this, then plus, and then we have the third one. The third one is this, okay, this is W transpose B. So W transpose B d omega is omega, and this is equal to 0. And this how we did? By what? By 3 plus 4. So okay, so by 3 plus 4, what does that mean? So we have seen these equations, we call it this is 3 and this is 4, we combine them together. Of course, how we combined, we have worked out separately. So for this plus this we work out here, then this plus this we work out here, for this and this we work out here, right, till here. Okay, so for this one we work out the whole thing here to here, and then finally we get this equation. So this is the what the weak form is, yeah. So we can write this one, right. So this is the weak form. So we got the weak form. Okay. One thing I realize now that I should not have written like this one. There is something is wrong here, because if you see here, the strong form has this one. So what is the meaning of this? This actually means that this is being differentiated, yeah. So in a strong form it should not be differentiated, in the weak form it should not be differentiated, so rather W has to be differentiated. So we should not write, so instead of writing like this one, we should write actually like this one only, okay. So this one is not good, because this means that this is going to operate on this. This we don't want. We want basically in the weak formulation we have the differentiation of W itself. So this one is correct, but not this one, okay. So that means we are going to strike it out. So not this, okay. So not this one, we want this, okay. And similarly we are going to replace here. So we will not use this one, so rather we are going to use instead of that we will use del S W and transpose of that, yeah. So I am going to write it again, okay. So the final form, the final, not final, we will also work have to apply the boundary conditions. So we say the weak form basically is this first. So okay, so we have this let us write make the correction first, and then we will do next. So we have this as W T tau and n. So W T tau and n, okay. So d gamma, okay, then minus, and we should have transpose of that, and then sigma. So del S W, so del S W, okay, transpose of that, sigma, and d omega, okay, then minus, so not minus but plus, WTB plus, so WTB d omega, okay, and that will be equal to 0. So we have written like this one. So this is what it should be, because this tail finally we will have the requirement of smoothness of this one, the required smoothness will reduce now, because there is no differential here, right? Sigma I will have del u over del x, okay. So we will see that, we have to see basically. So we have this one, yeah. So and this is how this makes sense now, because on the weight we have this operator which is being applied. Okay, so this is what the weak form is. Now we have to apply the boundary condition. And we know that, see here, boundary condition, we know that W will equal to 0 where u is given, right? So where u with displacement is given, yeah, and otherwise, and also we know that there are two kinds of boundaries, yeah. So one is gamma u where u is given, the another is gamma tau where gamma t where the traction is given, right? Traction is given t, right? T tilde is given. So that means, and how do we write there? So so this one we have to apply. So that is on gamma u, and so u equal to 0, and tau tilde n tilde equal to t tilde, which is given on gamma t, yeah. So the whole gamma is equal to gamma u union gamma t, right? Okay, so that means the whole thing, this one we can write it as, so just this, or the whole equation we can write as, so you know that this has two parts. One is gamma u where u is given and hence w equal to 0, so the whole thing will be 0. The second is gamma t on which this is given, and hence tau times n becomes t tilde. So w transpose and t tilde only, yeah, and that will be integrated over gamma t now, yeah. So meaning that this equation now will turn to, after applying the boundary condition, will be gamma t, and then we will have w t transpose t tilde t gamma, right? Then we have minus, yeah, and then we have omega del S W transpose sigma this omega plus omega W transpose B tilde d omega is equal to 0. So this is the equation after applying the boundary condition. So this is the final weak formulation.